The birth of the Sun, a cosmic odyssey. The Sun as a celestial phoenix. The Sun, our life-giving star, is a dynamic fusion reactor that has illuminated the solar system for 4.6 billion years. Its origins, however, stretch back to the remnants of ancient stars and the chaotic collapse of a primordial molecular cloud. This documentary explores the Sun's formation in granular detail, unraveling the physics, chemistry, and cosmic events that shaped its birth. Chapter 1: Cosmic Context, the Interstellar Nursery. The stellar life cycle and the interstellar medium. Stars are born from the interstellar medium ISM, a diffuse mixture of gas 99% and dust 1% permeating galaxies. The ISM is primarily hydrogen 70% and helium 28%, with traces of heavier elements, metals, and astronomical terms like carbon, oxygen, and iron. These metals, forged in supernovae and stellar cores, are critical for planet formation. Molecular clouds, dense regions within the ISM, serve as stellar nurseries. These clouds are cold 1050 K and dense 100 to 1000 molecules per cubic centimeter, allowing gravity to dominate over thermal pressure. The Sun's progenitor was likely part of a giant molecular cloud GMC spanning dozens of light years, with a mass thousands of times that of the Sun, triggering collapse. Supernovae and shockwaves. Star formation begins when a molecular cloud fragment becomes gravitationally unstable. This instability can be triggered by supernova shockwave explosions from nearby massive stars, compress gas. Spiral arm density waves. Galactic rotation hurls clouds into dense regions. Turbulent supersonic gas motions create overdensities. Isotopic evidence in meteorites, for example, aluminum-26 suggests a nearby supernova injected material into the solar nebula just before the Sun's formation, jump-starting collapse. Chapter 2: The Solar Nebula and Gravitational Collapse. From cloud to protostar, the gene's instability. The collapse of a cloud fragment follows the gene's instability criterion. When a region's gravitational potential energy exceeds its thermal energy, it collapses. For the Sun's precursor, this required mass 1 solar mass m, radius 10,000 astronomical units O, temperature 10 to 20 K. As the cloud contracted, conservation of angular momentum flattened it into a rotating disk, the protoplanetary disk, while the core accreted 99% of the mass into a central protostar. Accretion and the protosun's growth. Over 100,000 years, the protostar grew via accretion. In falling gas collided at supersonic speeds, converting kinetic energy into heat. This raised the core temperature to approximately 1 million K, emitting infrared radiation obscured by the dusty envelope. Magnetic fields played a key role, channeling material along field lines and driving bipolar jets, a hallmark of young stellar objects YSOs. These jets, observed in modern analogs like HH-212, regulated angular momentum, preventing the star from spinning apart.